Let me pull up again that contrast between classical computing and quantum computing, and let's see if we can build up something of a more representative mental model. It is true, of course, that data in a classical computer looks like a series of ones and zeros, and at a higher layer of abstraction, that might represent an actual data type, like an integer or some text, and at a lower layer of abstraction, those ones and zeros represent some actual thing in the physical world, like voltages across a capacitor or something like that. Now, these same layers of abstraction provide a pretty helpful framing when we discuss quantum computing. Over there, there's also some underlying physical measurement, and again, you represent the outcome of that measurement with some sequence of ones and zeros, and again, this might implement some actual data type that you care about, like a number. This symbol that I'm showing, by the way, is called a ket. I'll explain it properly in a couple minutes, but for right now, just think of it as conveying that something is coming from a quantum computer. Let's start things off with a description of quantum computing through the lens of that middle layer of abstraction, meaning we're going to postpone all of the underlying physics for now, which is a little bit like teaching computer science without discussing hardware. In a classical computer, there's no need to distinguish between the state of memory and what you read out from the memory. Both of them just look like the same sequence of bits. But it's a very different story in a quantum computer. Our main job today is going to be to understand something called the state vector, which is continuous. This is the thing the computer actually operates on, but it has a very unusual relationship with the values that you actually read out, those discrete sequences of bits.